Moreover, in the DRAM industry, it's completely different than it was just a few years ago. When I started, I think there was 15 different DRAM manufacturers. Now there's in practice 3 large ones and a couple of specialties. So the industry has massively consolidated, massively. That consolidation has led to price stability. The price stability has led to improved profitability, and improved profitability has led to higher stock market prices, and that's all good for the industry, but it is also something where there is not the investment necessarily to look at all of those advanced technologies. And most of the larger companies are shifting their investment from DRAM to flash. Now, when the big companies shift, you should think about that as an opportunity, not necessarily as something wrong. And the last is that there are some very interesting emerging technologies, new bit cell technologies, that can fill both the lower cost gap and have performance that's approaching that of DRAMs. And maybe if those new technologies come into play in the next couple of years, which I think most people believe they will, there's going to be an enormous opportunity to create novel systems. Of course, the big DRAM manufacturers will likely own that space and produce these new technologies, but it doesn't mean that smaller companies can't innovate at a module level, at a subsystem level, at a system level to integrate those and produce very superior price performance targets. So here's a chart from Micron, my good friend Mark Durkin, the CEO. And it shows from their Analyst Day presentation the 9th of August of last year, 2013, their investment from a DRAM and a flash standpoint. They don't tell the total on here, but just the percentage. And as you can see from 2005, the DRAM investment most was about capacity expansion. That's in the blue. But today, it's almost all about technology migration. So their statement to the world is that they are not going to produce a lot of additional capacity to produce new DRAMs other than those that are inherently achieved through improvement in technology and technology scaling, which, as I told you, is going to be difficult. Flash, however, is just the opposite, where the industry is continuing to expand. In this particular case, Micron is expanding greatly, and it's about a 50-50 split down from capacity expansion, again, to minimize the type of oversupply situations that they've had in the past, but it's still much more balanced towards new capacity and capacity expansion than technology migration. So clearly, this player, and I think if you went and found all of the other major players, they're doing almost exactly the same. So the industry is going to support profitability for a long period of time. That profitability is an opportunity for all of us. So let me briefly talk about some of the emerging technologies. Those material scientists, electrical engineers in here will find them particularly interesting. I'm not going to go through any of that physics or chemistry, but I would encourage you to do it, especially as you're thinking about new ways to innovate at a semiconductor level. The first on the left is phase change. And in this particular case, you change the phase of the material as you apply a current. That changes the dynamic electrical properties. And if you can do it fast enough, you can write a 0 or a 1 and interpret it, and you get the same type of behavior as a non-volatile. And some of these materials that they use, the phase change is quick enough that you can actually approach DRAM-like properties. The same thing with STT-MRAM. That stands for spin, torque, transfer, MRAM, magnetic RAM. In this particular case, what you're doing is changing the magnetic dipoles in the material, and by switching it, again, changing the state of the material. And that can happen very, very quickly. And as it happens quickly, you can get DRAM-like data rates at the benefits of non-volatile. So a very, very interesting combination. The last one happens to be our favorite. We've invested in this. We've acquired a company where we focus on the architectures and way to look at it, and that's resistive RAM. That's a little bit different. That's where by applying a voltage, you can actually grow little dendritic fingers that can change the resistive properties. And again, if you do that quick enough, you're able to have very rapid data rates. So all three of these technologies are vying for the entrance into the marketplace. I think all of them have potential. There's many companies that are investing them in a much broader way. And I'm not necessarily suggesting that in India you would want to set up a fab to design on one of these, although you might. But it's certainly something to think about at a system level in different ways, that as these new technologies roll out in the coming years, that you can change the architectures, improve the cost performance point, and for the first time in 30 years, a very stable memory industry, make a lot of money for your company. So this is something that the DRAM industry uses often. It's a very interesting chart. It doesn't necessarily convey some of the important parts, however, which is why I drew that little dashed circle around in the center. So on the top, they talk about level 1 caches and level 2 caches. It's almost always fast SRAM. It can be on chip, so electrically the most close. It can be off chip, a little electrically further, but still just a couple of clock cycles away, and something that you can access and with a reasonable amount of density and a reasonable working set from a software standpoint, you can have good performance. Of course, a lot of the things oops, it's not. Seems it must be a Mac to PC conversion problem. Sorry for the, the lines. So in terms of the main store, however, in DRAM, you have a much wider, much lower cost optimum. It's something that has a lot of performance attributes still compared to non-volatile, but it's not nearly as fast as the SRAM technologies, and therefore tends to be an intermediary. Below that you have non-volatile, which we've talked about, hard disk drives, and optical. So what it's supposed to say on the right is that the cost per bit goes down as you go down the stack. The performance, or the speed, goes up. That's the one on the left, as you go up the stack. And of course, the capacity, which is represented by the width of the triangle, is more as you go down, typically. The problem in the middle here is that there is a huge difference in read-write time. So how quickly you can access the memory from DRAM to flash. And as a consequence, it's unlikely, without these new technologies, that we can fill the gap. So once they are filled, however, there's a lot of performance potential. So let me bring it together and talk about addressing the challenges in just a couple of minutes. If there is one chart that you remember in this presentation as an entrepreneur, this is it. I think there's a lot of interesting information here, even if it seems on the surface that we're providing only a few key points. Let me systematically walk through it so you can understand. On the bottom is there are ways, and in fact our company Rambus is doing it, to enhance the standards through innovative design in signal and power integrity, and to be able to have much higher performance even at the current technologies. So it is possible to improve things. Our company is doing that. We're openly licensing this technology. I would encourage all of the great electrical engineers to consider doing that on your own, building businesses around it, because innovation is every place. Moving one step up in the lighter blue is memory systems. Here, I mentioned briefly that there's a very big difference in how non-volatile memory is used in systems and how DRAM is used in systems. Non-volatile, everybody accepts that, geez, it's not going to have the endurance, the bits are going to fail, and we have to find ways through the controllers to actually take that into account. In DRAMs, the industry doesn't do that. The industry expects everything to be almost perfect, and as a consequence, the barriers to introducing the two technologies are very high. And in the future, especially as I showed that scaling problem, this huge aspect ratio where it's hard to build, there's going to be more defects. It's going to be harder to introduce new technologies. Well, imagine if you applied some intelligence to the memory modules, and through that intelligence in the memory modules, you could kind of deal with these problems. There are a lot of companies working on this type of problem. We are one of them. I would encourage you to think about this. It sounds like a small business, but over time, it's likely that these managed DIMMs with specific features is something that will be used in every PC, not just in servers. So something for you to consider. Moving up the stack one more, Whether you have these managed memory systems or you just completely rethink how memory systems are working, you can change the actual structure of things in the data center and think about novel memory appliances. Today, the industry tends to think about three things: CPU compute, disk space, and networking. And depending on the type of application you're running, they configure it differently based on those three things. Now, the interesting part is when you think about the compute side of it, that usually is included a processor and the level 2, the SRAM, and the DRAM all in one, and that's a unit of commerce. That is not a required architecture, however. You can look at things completely differently and put together memory appliances where you can have massive amounts of DRAM accessible for applications. And some of the data mining applications, the big data applications, from our analysis, this is a very interesting area to investigate. Moving up to the top, and this is for those with a lot of money to invest, is new memory bit cell technologies and hierarchies. It's the resistive RAM, the magnetic RAM, or the phase change memories that I discussed before. It's not something that we are trying to work on. It is something that the industry is. But once these new memories are out, as I said, there's huge opportunities. And even if you have the money to invest in a fab, it's an interesting way to think about getting into a new space that for the first time, as I said, in 30 years, is probably stable and going to be stable continuously.